So we're going to be looking at ways to build organic molecules, and this will require a tremendous amount of knowledge which you have learned in previous chapters, especially in chapter 9, where you looked at the reactions of alkenes, and in chapter 10 when you looked at the reactions of alkynes. Now, when building a home, you must have the right tools, and in the same way, when building molecules, you need to have the right tools. And the tools we are referring to are nothing more than the chemical reagents. Of course, the materials that you're going to use will be the reactants, but to carry out the transformation or the conversion of the reactants to the products, you need chemical reagents, and these are the tools necessary for you to be able to carry out synthesis. Now, to be able to optimize your synthesis, you need to know how the tools work. For instance, if we are going to look at this example, this is an addition reaction. This is an addition of bromine molecule to the double bond, and this will proceed easily in the dark with carbon tetrachloride as the solvent, bromine molecule as the reagent. Now, this is something that we covered in chapter 9, so this is just going to be review. Now, you may want to be able to solve a one-step synthesis problem by matching the reaction. Be able to solve a one-step synthetic problem by matching the reaction with the reaction in your textbook. But the truth is, by the time you begin to see very complex synthetic problems, you find out that trying to match reactions with the type of reaction in your textbook with the kind of reactions you are giving will be impossible. So to be able to carry out any transformation, you need to know what the reagent is doing. Okay, you need to know what the reagent is doing. You need to know the radioselectivity of the reagent. Is it Markovs or anti-Markovs? You need to know the stereochemistry. Does it go anti or does it go syn? Does the reaction proceed with racemization? I mean, these are things that you need to know about. You see? So you need to know what the reagent is doing. This is very, very important. You need to know what the reagent is doing. Now, there are some basic steps to be able to know how to solve synthetic problems. Okay, the very first thing, you need to analyze the structure of the reactants and the products. Look at both of them, yeah, right, and see how the functional groups have changed, right, or if the number of carbons have changed. And then you're going to use the reaction and mechanisms you learned to determine appropriate reagents and conditions. So you can see, for instance, this example is the anti-Markov addition. Is the anti-Markov addition of HBr to an alkane. You see, and of course we see that it goes anti with the bromine going to the more substituted carbon, right? So this is something you need to know. You need to know from the product, you can tell what kind of reagent was used. That's basically what you need to know. Now, let's review some synthetic tools we learned so far in chapter 9. For instance, you learned that if you want to move the halogen, you have to first carry out an elimination, and then you carry out an addition. Okay. Once you carry out an elimination to give the ZSF products, the next thing is to carry out an addition to give the anti-Markovs product. You see, so really depending. So the radiochemical consideration in this process is vital. Okay, it's really vital. I have some examples here which you can inspect. You can see that the bromine has shifted. It has shifted. That shifted from the primary carbon to the tertiary carbon. You see? And so the first thing you want to do is do an elimination, and then you do a Markovnikov addition. Okay, here you can see that the double bond has shifted. The first thing you want to do an addition. You want to do an Markovnikov addition, and then you do an elimination to give the Zaitsev product. See, you want the Zaitsev product. You see, so depending on what you're asked to do, right, you just have to know what the reagent is doing. Okay, look at this example here. Again, you can see that the halogen has shifted. It's a second degree. It's on the second degree carbon, but here it's on the third degree carbon. So the first thing you want to do is do an elimination. So you do an elimination, you get the Zaitsev product, and once you get the Zaitsev product, you can now do a Markovnikov addition to get your tertiary alkyl bromide. Okay, now if once you get to your Zaitsev product, you can always go back in an anti-Markovnikov fashion using HBr and peroxide, just like we learned in chapter 11. Now you can see again, if you look at this example here, right, the bromine has shifted. It went from a secondary to a primary carbon, or primary alkyl bromide. You see, so because it's primary, you want to get the less substituted or the terminal alkene. So you need a bulky base for that. You need a bulky base. It's a bulky base. You need a bulky base, so you get the Hofmann product. And once you get the Hofmann product, you can do an anti-Markovnikov addition of HBr to give your primary alkyl bromide. Okay. Now that's the case of a halogen. What if you're dealing with an alcohol? Here we have a second degree alcohol, and we have here a third degree alcohol, and we have here a first degree alcohol. How do you go from a second degree alcohol to a third degree alcohol? Okay, again, you have to do an elimination. You get the Zaitsev product. Notice that this is tosyl chloride. Tosyl chloride is used to convert the OH to OTS, or the tosylate, right, which becomes an excellent leaving group. And so in the presence of a base, the reaction can go E2 to give exclusively the Zaitsev product. Now once you get the Zaitsev products, you want to do an acid catalyzed hydration. So this is an acid catalyzed hydration to give the third degree carbon. Now, once you arrive at the Zaitsev product, you can always go back to second degree alcohol by doing a hydroboration oxidation, which we know goes via an anti-Markovnikov mechanism. Okay. Now, if you want to get to this first degree alcohol, you will need first to make the Hofmann product. Okay. So you convert the OH to a good leaving group, just like we did in the case of the tertiary alcohol. Use a bulk, but this time you'll have to use a bulky base because you want the Hofmann product. Okay, and then you do an anti-Markovnikov hydroboration. So this is an anti-Markovnikov hydration. You see, so that's an anti-Markovnikov hydration. See. Now, so you can also have a situation whereby the double bond is moving. As you can see here, we have the Hofmann, this is the Zaitsev product, and you may want to make the Hofmann product, right? This is is the most substituted double bond you can get. And so the first thing you want to do is to do a magnetic conversion. Put the bromine there, which is a good leaving group, and then with the aid of tertiary butyl potassium tertiary butoxide, you can make the exocyclic double bond. Okay. Now, if you wanted to make a different, less substituted double bond, like this one, then again you have to do the anti-magnetic addition. Put the bromine on the less substituted carbon, right, and then do an elimination with a bulky base to put double bond there. So it really depends on what you're trying to do. But you notice that if you want the more substituted double bond, then you have to use a thermodynamic base like sodium methoxide. But if you want the less substituted double bond, then you have to use a kinetic base such as potassium tertiary butoxide. See? So it really depends on what you are trying to make. In chapter 11, we learned how to introduce a halide via a radical bromination. We say that this reaction is very selective. In the presence of a primary a primary carbon, right, and a tertiary carbon, the reaction goes exclusively tertiary. Now, once you are able to introduce the halogen or the halide, then you can control the degree of saturation. You can control the degree of saturation. Already we know that if you have an alkyne or a triple bond, you can do a hydrogenation with Linda's catalyst or dissolving metal reduction with ammonia to give sodium and ammonia to give the alkene. Now, once the alkene has been made, you can go backwards by doing an addition of molecular bromine, do an elimination, and you get your alkene back. I'm sorry, you get an alkyne back. I'm sorry. So this is an alkyne. You get your alkyne back. Okay. Now, once the alkene is made, you can easily go and make the alkane. Right. If you want to go back to the alkene, all you need to do is put a good handle like bromine, and you do an elimination, and you get double bond. So you see, you can control the degree of saturation. See, you can control the degree of saturation at any time. Now, functional group transformations. If you see here, we're asked to give necessary reagents for the functional group transformation here. Notice that prior to, you should have had a double bond here. So you should have had a double bond here. So to go about this, first of all, you need to put a good handle like a bromine. So you do that using NBS and light. And then you do an elimination with a thermodynamic base to get the alkene. And from there, you can do the dihydroxylation with osmium tetroxide followed by sodium hydrogen sulfide hydrolysis. And you get your corresponding diol. So this is something, this is just review from what we talked about. Okay. Now, there are many important molecules that have complex carbon skeletons, and the ability to design synthesis that produce a desired carbon skeleton is highly prized. Now, some reactions will increase the number of carbons. We know the different reagents that will increase the number of carbons. This includes things like the Grignard, which we're going to look at shortly, the Gilman reagent, and what we looked at last semester was the alkylinide anion. That's very important. This is a great way to form carbon-carbon bonds. While some other reactions will decrease the number of carbons on the molecule. Example is an ozonolysis. Okay. Now, so just note those reactions. So far, we have learned only one transformation that increases the number of carbon, and that's the alkylinide, whereby you can increase the number of carbons of an alkyne by converting it into its conjugate base. In this case, you're adding 3 water carbons with an alkyl halide, and so it goes via an SN2 reaction, and you get 7 carbon alkyne. Okay. We have also learned how to decrease the number of carbons via an ozonolysis. So you do an ozonolysis and then followed by DMS or zinc and acid hydrolysis, and you get 4 carbons and 1 carbon. In future, we will discuss more reactions after the carbons have been altered.